There is this very specific phase in a developer's career. I could call it the invincibility phase. It usually happens right after you discover a new library or maybe a standard function that completely automates something you've been doing manually for months.
Oh yeah, I knew the exact one. It's that feeling of unlocking a cheat code in a video game.
Exactly. You stop writing these massive nested for loops, you replace 50 lines of boilerplate with just one function call, and you suddenly feel like a wizard. But here's the catch, and it really is the central theme of our deep dive today. Sometimes those magic spells just backfire. And when they do, they don't just break your code, they can fundamentally destabilize your entire application.
Right, because using a tool that you don't fully understand is, well, it's kind of like trying to drive a Formula One car to the grocery store. I mean, it works right up until you hit a speed bump or until the engine just overheats in the parking lot.
And today we're talking about one of Python's most seductive speed bumps, the deep copy function. Yeah, it promises to clone literally anything. You just point it at an object, run it, and get a perfect independent copy. But as you're going to find out today, there's a whole class of vital system-level objects that absolutely refuse to be cloned.
And honestly, for good reason. If you could clone them easily, we would have way more security holes and data corruption issues than we already do.
To navigate all of this, we are digging into a fantastic source article today. It's titled The Secret Life of Python, the Uncopyable Deep Copy, and that is by Aaron Rose, published over at the Tech-Reader blog. The article uses this really great narrative structure. It follows a junior engineer named Timothy and his senior mentor, Margaret, to basically explain why your code just crashed with a massive type error.
And what I really appreciate about this specific source is that it uses that crash to teach a much broader architectural lesson. It isn't just about Python syntax at all. It's about the fundamental difference between pure data, like your strings and your integers, and actual system resources, like network connections.
Right.
And that is a distinction that trips up even very senior engineers all the time.
So our mission for this deep dive is to save you from that dreaded wall of red text. We are going to explain why you cannot photocopy a phone call, why zombie objects are an absolute debugging nightmare, and how to use the builder pattern so you handle your resources correctly every single time.
Sounds like a solid plan.
Let's start with the setup here.
Yeah.
We have Timothy. He is the protagonist of our source article, and he is squarely in that invincibility phase we were just talking about. He has just wrapped his head around copy.deepcopy.
Which, to be totally fair to Timothy, is a genuinely powerful tool. In Python, a standard assignment is usually just a reference. Like if I say list A equals list B, I haven't actually created a new object. I've just slapped a new name tag on the exact same underlying list.
Right, they point to the same memory.
Exactly. So if I change A, then B mysteriously changes too. And that trips up beginners constantly. So deep copy fixes that by recursively walking through and creating a brand new, fully independent object.
It walks all the way down the tree of data and clones every single leaf. So Timothy is feeling pretty powerful. He is writing a script to back up a tournament database, and he needs to run some heavy experiments on the data without risking the live production database.
Makes sense.
So his logic is pretty straightforward. He thinks, I have this active connection object, I'll just deep copy the whole thing. Then I'll have this perfectly safe sandbox connection to play around with.
It's a very logical thought process for a junior developer. He wants isolation. He wants a safety net. He just figures, if I clone the object, I clone the connection. Done and done.
So he hits run on the script. He expects a nice, clean clone. And instead, the console just explodes. The article literally describes it as a wall of red text.
The classic stack trace of doom.
Yeah. And at the very bottom, there's this incredibly cryptic error message. It says, type error, cannot pickle underscore thread dot lock object. Now, if I am Timothy, I am staring at this screen thinking, pickles, threads. I just wanted to copy a database connection. What in the world just happened?
Yeah, that error message is actually Python pulling back the curtain a little bit too far. To understand why it failed, you really have to understand how deep copy operates under the hood. It relies entirely on Python's serialization protocol, which the language developers decided to call pickling.
Okay, let's pause right on that word. Pickling is really just Python's cute, slightly confusing name for turning an object into pure bytes, right?
Essentially, yes. To copy a really complex object, Python tries to melt it down into a stream of ones and zeros, a byte stream, and then it takes that stream and reconstructs it into a new object somewhere else in memory.
Like a teleporter.
Exactly like Star Trek teleportation. You deconstruct the original into pure energy, or bytes in this case, and then you reconstruct the copy somewhere else.
But the error explicitly says it cannot pickle a thread lock.
Right. And this is exactly where Margaret, the senior mentor in the story, steps in. She points out to Timothy that he has officially found the edge of the map. He is trying to serialize something that simply has no digital representation in terms of pure data.
This is the core distinction the article brings up. Data versus resources. Can we drill down on that for a second? Because, on a computer, isn't absolutely everything just data? At the end of the day, it's all just bits on a hard drive or in RAM, right?
In a strictly physical sense, sure, it's all electricity and silicon, but functionally, not at all. Think about a simple list of users. That is data. It sits quietly in your RAM. It is entirely self-contained. If you write those exact bits to a hard drive, turn off the computer, and then read them back a year later, the list is still exactly the same list. It doesn't depend on anything outside of itself.
Okay, that makes sense. It's inert.
Exactly. Now, think about a live database connection. What is that, really? It isn't just a bundle of static variables. It actually represents an active, currently negotiated state between your Python script, the operating system, the network card, and some database server sitting in a rack somewhere else.
It's a whole ecosystem.
Right. It involves open file descriptors, active network sockets, and authentication tokens that are only valid for this one specific session in time.
So it's a relationship. It's not just a fact you can write down.
Precisely. It is a live link. And that is exactly why the error mentions a thread lock. A lock is an OS-level mechanism used to control access to that relationship. So two threads don't try to talk over each other at the exact same time.
No.
You simply cannot copy a lock. Think of it like a physical key to a room.
Okay.
If I have a key and I copy it, I have two keys. Great. But if I am currently holding the physical door handle, physically preventing anyone else from entering the room, how do you copy me holding the door handle?
No, we can't.
You can't. It is a temporal state. It's an action happening right now, not a static data structure.
Margaret uses a really brilliant analogy in the article to make this concept land for Timothy.
Oh.
She asks him to imagine he has a piece of paper with a list of his friends' names on it.
Right, which represents pure data. Easy to copy.
She says, you can photocopy that list all day long. You can fax it. You can email a scan of it. The underlying information remains perfectly intact.
Yeah.
But then she pivots. She asks him, what if that list implies a live phone call to your friend?
And that is the clicker. That is the moment it makes total sense.
If you are currently on the phone with someone and you take your physical smartphone, put it face down on a glass photocopier, and press copy, what do you actually get out of the machine?
You get a flat, useless picture of a phone. You definitely do not get a second person on a second phone line who is magically now part of the conversation.
You don't clone the human being on the other end of the line.
No, you don't. And that is exactly what deepcopy tried to do. It saw the database connection object, which acts just like that smartphone, and blindly tried to clone it. But it hit the socket, the actual active voice line, and the thread lock, and the pickler just threw its hands up. It realized, I cannot turn an ongoing live conversation into a string of zeros and ones.
So the crash is basically the photocopier jamming and sparking because you literally tried to shove a physical telephone wire through the glass plate.
That is a very visceral image, but yes, exactly. It is the operating system stepping in and saying, this is way outside your jurisdiction, Python. The OS owns that physical connection, not your script. Python just has a little handle pointing to it. You cannot clone the handle and just expect the OS to magically run a new physical wire to the server.
Now, this leads into the part of the story that I personally found really fascinating. Timothy, being a typical programmer, immediately starts looking for the hack. He looks for the workaround. He asks Margaret, okay, so it crashed. But what if it didn't? Wouldn't it be so much better if Python just copied the parts it could and quietly ignored the lock?
Oh man, the best effort fallacy. That is such a dangerous road to go down in software engineering. Just ignore the errors and keep barreling forward.
Margaret calls this the zombie corruption scenario, which sounds super dramatic, but she seems dead serious about it.
She is, and she absolutely should be. Let's play out his scenario. Imagine if Python actually suppressed that pickling error. Imagine it said, okay, I can't copy the live network socket, so I will just skip that little part, but I will happily copy the text variables that say status is connected and user is admin.
So you get a brand new object returned to you, and it looks exactly like a valid database connection. It has the right username string, The right IP address stored in its internal variables.
Right. It walks like a connection, it quacks like a connection. But
Well,
if you actually try to use it,
dead silence.
or much, much worse, this is the zombie she's talking about. It is a hollow shell. If you try to run a SQL query through it, your program might just hang indefinitely because it is waiting for a TCP response on a socket that literally does not exist.
That sounds incredibly annoying to debug.
It is a nightmare. But here is the true worst-case scenario. Suppose deepcopy was really aggressive. Suppose it managed to copy the actual file descriptor number. That's just the basic integer ID that the operating system uses to identify the open socket.
Oh, I see exactly where you were going with this. Now you have two distinct Python objects pointing to the exact same physical resource.
Exactly. Now you have two phones that think they control the exact same phone line. You send a drop table command on the sandbox copy, and it interrupts the live data stream of the original production object. You could corrupt an ongoing transaction, completely crash the actual database server, or just get incredibly weird interleave data coming back.
It's like two people trying to type an email on the exact same physical keyboard at the exact same time.
That's a great way to put it. So that wall of red text, that loud, obnoxious crash Timothy saw, it isn't a failure at all. It is a critical safety mechanism.
It's the guardrail actively preventing you from driving your car off the cliff. It is Python flat out refusing to hand you a broken, dangerous tool.
And honestly, as developers, we should be deeply thankful for those hard errors. Explicit failure is always, always better than silent corruption. A loud crash you can find and fix in 5 minutes. Corrupted data might go entirely unnoticed in your system for months.
Okay, so we have firmly established that deep copy is absolutely the wrong tool for any kind of system resource. But Timothy's original problem is still very real. He does actually need a second database connection. He needs that isolated sandbox environment to test his backup script so he doesn't break production. So if he can't copy the connection, what is he actually supposed to do?
This brings us to the core architectural lesson of the whole piece. Margaret introduces him to something called the builder pattern.
It sounds kind of fancy, but in the context of the article, she simplifies it beautifully. She tells him, you don't copy the object, you copy the instructions.
Don't copy the journey, copy the map. It is such a fundamental shift in how you think about state. If you want two identical cakes for a party, you don't take a finished baked cake and try to clone it molecule by molecule in some sci-fi lab. You just take the original recipe and you bake a second cake.
That makes perfect sense. So how does this actually look in standard Python code? Because the article gives a very specific before and after comparison.
Right. So the wrong way, which was Timothy's initial way, was writing backup_con equals copy.deepcopy, passing in original_con. That triggers the crash. The right way, the professional solution, involves completely separating the configuration from the active connection.
Configuration meaning the host IP, the port number, the login credentials.
Exactly. That stuff is pure data. That stuff is entirely pickleable. That stuff is your recipe. So instead of copying the live object, you create a factory function. Let's just call it create_connection. And you pass it a simple dictionary of those config settings.
And then that function handles all the messy, real-world work of opening the sockets and performing the server handshake.
Correct. So when Timothy wants his sandbox environment, he doesn't even touch the existing production connection object. He takes the config dictionary, the recipe, and he just calls create_connection, passing the config a second time.
And boom, he gets con 2.
And con is a perfectly fresh twin. It has its very own dedicated network socket. It has its own isolated thread lock. It negotiated its own brand new session with the database. It is 100% independent.
So if he messes up con 2, say he runs a command that drops a table in a sandbox, con 1 is completely unaffected.
They're totally safe. And honestly, more importantly than just the safety, the code is suddenly highly readable. Anyone reviewing that code and seeing create_connection knows exactly what the intention is. Oh, we are spinning up a brand new system resource. Whereas if you see deep copy, it's highly ambiguous. Are we copying state? Are we sharing a connection pool? It's just muddy.
This approach essentially forces you to treat resource setup as a standard, repeatable process, rather than a fragile one-off event.
Which is really the hallmark of any scalable system. If you cannot easily recreate your current state from scratch using just your config, you have a very fragile architecture. If your application relies on some magic connection object that was created 5 hours ago and nobody knows how to replicate it, you are in massive trouble the second that connection drops.
Now, toward the end of the article, Margaret provides what she calls Margaret's cheat sheet. I think this is just a perfect mental bookmark for our listeners. It is a really quick litmus test to know exactly when to step away from the copy library.
Let's run right through it. It is the very simple binary choice.
Category 1 is pure data. So we're talking about lists of strings, dictionaries of user high scores, simple data classes that just hold static information.
Deep copy is your absolute best friend here. Big green check mark. These are just bits sitting in memory. Python can serialize them, move them around, clone them effortlessly. It works exactly the way you expect it to.
Category 2 is resources.
This is the danger zone. Open files.
Nope.
Database connections.
Definitely not.
Network sockets, thread locks, multi-processing pipes. Basically anything that involves an open handle negotiated with the operating system.
Big red X.
Deep copy will fail, and as we've discussed, it really should fail. If you ever find yourself trying to import copy to duplicate these things, just stop. You are trying to photocopy a phone call.
And the solution for category 2 is always the builder pattern.
Always. Create a factory function. Pass the pure configuration data in. Create a fresh, brand new instance.
There was one little advanced note in her cheat sheet that I actually found really intriguing. Margaret mentions that objects can technically define a special double underscore method called dunder deepcopy.
Yes, because in Python, practically everything is customizable. The original author of a database connection class could, entirely in theory, write their own dunder deepcopy method. And inside that specific method, they could write code that secretly reads the internal config and spins up a brand new connection behind the scenes, essentially automating the builder pattern we just spent all this time talking about.
So it would look like a simple clone to the user, but act like a full rebuild under the hood.
Technically, yes, it is possible, but Margaret and I strongly agree with her on this, strongly advises against relying on this kind of trick.
Why is that? I mean, it sounds super convenient. If I can just write copy parentheses con and it magically works, isn't that a good developer experience?
It feels convenient in the moment, but it's what we call magic. And in software engineering, magic is usually bad. If I am reading your code and I see copy connection, I am going to assume that is a chief, purely local memory operation. I assume it takes maybe a few microseconds. If that operation actually triggers a full network handshake, negotiates SSL certificates, and takes 200 milliseconds, that is hidden behavior. That is a massive hidden side effect.
I see. You're hiding a very heavy, complex operation inside a deceptively light wrapper.
Exactly. And one of the core tenets of the Zen of Python is explicit is better than implicit. It is almost always safer and cleaner to be explicit. Just call, create new connection. No surprises for the next developer. If your code is doing network I/O, you want to plainly see that it is doing network I/O.
It really all comes down to respecting the complexity of what you're actually working with. I really loved Margaret's closing piece of wisdom in the story. Timothy is looking at his newly fixed code. He has completely ditched deep copy, and he's happily using the builder pattern. And Margaret tells him, the best engineers don't look for a single tool that does absolutely everything. They look for the right tool for the specific material they're currently working with.
That is the exact transition from a junior mindset to a senior mindset right there. When you first start out, you just want the universal hammer. You want the one magical function that solves every single problem. And deep copy really feels like that hammer at first.
He'll just clone the universe. Problem solved.
Exactly. But as you grow and gain battle scars, you realize that context is king. You treat data like data, and you treat resources like resources. You start to respect the fact that the operating system isn't just a dumb bucket of memory you can dip into whenever you want. It is an active participant that constantly needs to be negotiated with.
It's a lesson in boundaries, really. Just because you can easily import a library in Python doesn't mean it overrides the physical laws of the universe, or at least the laws of the OS kernel.
Very well said. And frankly, understanding why something fails the way it does is usually way more valuable in the long run than just knowing the syntax to make it work. Timothy learned way more about system architecture from that one crash than he ever would have if the copy had just magically succeeded.
Totally true. He learned about serialization, OS locks, the builder pattern. That is a highly productive failure. Now, before we sign off today, I have to mention the teaser at the very end of the source article, because it looks like poor Timothy is not out of the woods quite yet.
Oh no, the Python learning curve is steep and unforgiving.
The next entry in the blog series is titled The Default Trap. And the tagline says, Timothy is going to learn that giving a Python function a default list is like sharing a toothbrush with a complete stranger.
Oh man, the mutable default argument trap. That is an absolute classic. That specific bug has bitten every single Python developer on Earth at least once.
Sharing a toothbrush is just a horrifying mental image for writing code.
It is shockingly accurate, though. It's a
Right.
total hygiene nightmare. You write the function thinking you were getting a nice, fresh, empty list every single time you call it, but you're actually reusing the dirty, populated list from the previous function call. It's sticky, it's gross, and it causes state bugs that are almost impossible to track down if you don't know what you're looking for.
I cannot wait to unpack that one in a future deep dive. But for today, here is our challenge to you, the listener. The next time you are looking at your code base, especially if you are doing any kind of system backups, multi-threading, or heavy state management, take a minute to audit your use of copy in deep copy.
Look closely for those zombies. Ask yourself the fundamental question, am I just copying a recipe, or am I actually trying to photocopy a freshly baked souffle?
And if you realize you are trying to photocopy the souffle, just stop, take a breath, and write a builder function. Your future self, and definitely your database administrator, will thank you. And really, I think this leaves us with a pretty profound thought to chew on. Yeah, this whole issue with deep copy highlights this massive illusion we all buy into as developers. We write variable equals connection, and we think we own it. We think the resource belongs to our script. But you never actually own a system resource. You were only ever leasing it from the operating system. Our code is just a very polite fiction layered over a chaotic reality of hardware and networks.
That is a great perspective. You're just holding a ticket. The OS still owns the ride.
Exactly. So respect the lease, build from scratch when you need to, and you will avoid that wall of red text. Thanks for diving deep with us today. Keep your connections fresh, and we'll catch you on the next one.